Now that we have an intuitive understanding of what a binary search tree is, let's give ourselves some rigorous definitions. So a tree consists of a set of nodes and a set of edges that connect those nodes, with the constraint that there's only one path between any two nodes. So let's see some examples. Here is a tree which has a set of one node and a set of no edges, so it's a tree. Here's a set with 3 nodes and 2 edges, and there's only one path between any 2 nodes. There's another. What do I mean by having multiple paths? Well, this right here is a set of 4 nodes and 4 edges, and as you can see, there are multiple ways to get from, say, the top node to the bottom. We could either take the left side or the right side. And then here is another example, right? So this one looks a little more tree-like, but it is not, because there are 2 ways to get from this top node to this bottom one. We can go downwards, or we can go up and around. Okay, so tree, 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 not a tree, not a tree. Now let's introduce the idea of a rooted tree. So a rooted tree is a tree where we pick one privileged node and say, hey, you're the root. So what does that mean? Well, every node except the root, once we define the root, so every node except the root has one parent, and we define that as the first node on the path from end to the root. Now I should note that a rooted tree is topologically the same thing as a tree. It's the same set of rules. It's just that we've picked one node that we're calling the root. And usually we'll draw the tree with a root at the top. Okay, so that's backwards from real world trees, but that's what we're gonna do. And lastly, a node with no child is called a leaf. So for example, C is a leaf. C's parent is B because B is the first node on the path from C to the root. And because a tree has only one path from any node to the root, there's no ambiguity. Now in a rooted binary tree, then every node has either 0, 1, or 2 children. Okay? And each of those children is a subtree. So for example, A has 1 child in this middle example, which is B. B has 1 child, which is C, and it has 0 children. On the right, we have a tree which is a rooted tree, where A has 2 children, B and B, and B has 3 children, C, C, and C, all of which are leaves. But this tree is not binary, so it's not a binary tree. Okay. So at this point, we've defined a tree, we've defined a rooted tree, and we have defined a rooted binary tree. Hooray, good. Okay, so lastly, we have the definition of a binary search tree. So a binary search tree is a binary tree with one additional property, known as the BST property, or binary search tree property. What is that? Well, it's that for every node in the tree, every key in its left subtree is less than X's key. And here you could think of key as the item in the node. And every key on the right subtree is greater than X's key. And this is a recursive definition. Okay? Binary search trees, in fact, are one of the most beautiful and natural examples of recursion in computer science, in my opinion. We see it in the definitions, we see it in the way that the code is written, and so here, let's see a couple examples. So right here is a binary search tree because dog, okay, that's the root here, has 2 children, bag, elf, and cat, and all of these are less. And on the right, we have flat, elf, and glut, all of which are greater. Now bag is itself also a binary search tree. It has a left child, which is elf, and a right child, which is cat. And everything on the left is smaller than bag, and everything on the right is larger. Here we have the another binary rooted tree, but in this case it's not a binary search tree because, well, while it is the case that ears, fish, and gut are all larger than det, fish is not larger than ears. Or sorry, fish is not smaller than ears, so it should not be on the left. Now one other little point of terminology here is that you'll notice I've added arrowheads here, and I did not have them before. That has no special meaning except to make it very clear who is the root and who is the child. So in this depiction, I'm drawing the arrows pointing towards the children, but sometimes you'll see diagrams that are the other way around. Now one important point about this ordering. The one that we give, it must be complete, it must be transitive, and it must be anti-symmetric. So what I mean by that is that given 2 keys, that the values inside, sorry, given 2 keys, that's the item inside of the node, so the keys P and Q, it must be the case that exactly one of P is less than Q and Q is less than P are true. Okay, so in that sense, they can't both be true, and they can't neither be true. And then transitively, we can't have that P is less than Q, Q is less than R. Or wait, what I meant to say is, if P is less than Q and Q is less than R, then that implies that P is less than R. Now you may ask yourself, like, what is an example of a relationship that would be transitive and anti-symmetric but not complete? And that would be, for example, like where you are in your family tree. So compared to your parents, you might say that you are less than, but compared to your cousins, there's just no answer. It's not a complete thing. You're like on different branches of the family tree. Possibly a bad example in the context of trees. Don't want to confuse you, but I just wanted to mention that the ordering we specified to actually make sense, it needs to be complete, transitive, and anti-symmetric. Now, one consequence of these rules is we cannot have duplicate keys. As you'll note, we said you cannot have P less than Q, you need to either have P less than Q or you need Q less than P. You cannot have any duplicates. And that makes the thinking simpler. And actually, interestingly, most real-world implementations follow this rule. So what I mean by that is you cannot have the word dog twice in your binary search tree. That would break the rule that one of these must be true. Okay, and it turns out it doesn't actually weaken the power of our idea. All right, so those are our key definitions. And so soon we'll be moving on to operations.